So let us start today's lecture. So we were talking about A to D construction of an A to D converter. So we talked about sample and hold circuit. Basically, the role of the sample and hold circuit is to hold an input until it is being converted by the ADC. ADC takes a few microseconds to convert a sample. So it takes a sample and sample and hold circuit uh, keeps that sample constant to the ADC. So today we'll go beyond sample and hold circuit into the actual ADC construction, how ADCs are constructed. So some important component of these ADCs are an AND gate, a DAC, counter, maybe a state machine, things like that. So all those components you are already too familiar with. So let us talk about those components. The first ADC we are going to talk about is called staircase ADC. Staircase ADC. जरा देख लेना यार ठीक है हाँ हाँ जी So staircase ADC. Uh, and so we are basically going to talk about this signal, where we know that the signal is coming from analog. Signal is coming from sample and hold circuit, SNH circuit, and this comes here and it gives you n bit output. And this is the actual ADC. Here you have a start of conversion signal, and here you have end of conversion signal. Start of conversion signal also goes to sample and hold circuit because it locks the input and takes the sample of the input and then it holds until the conversion is done. So what's inside this circuit? थोड़ा इधर करना. So inside this circuit, we have in this circuit over here, we have the first thing that we have is a comparator. Comparator. पढ़ा जा रहा है? So we have a comparator here. So here it goes, the input comes here, analog in. It is compared with another input. So this comparator is basically that plays the role of conversion. basic conversion. It is that gets us into the digital domain. So what's the role of the comparator? Basically, comparator is an open loop operation amplifier, and the comparator is the role of the comparator is that we have V in 1, we have V in 2. The role of the comparator is that if V in 1 is greater than V in 2, out is equal to 1, logic 1, which is equal to 5 volts. And if V in is less than equal to, if V in 1 is less than V in 2, then out is equal to logic 0, which is 0 volt. So this is the job of this comparator. So basically, this converts these two inputs into digital form. That's the first thing that brings the analog circuit into digital domain. So what now we need is a clock generator. Say we have a clock generator, clock that goes, say for example, this is 1 megahertz clock. This goes to, as I said, very important component, that is AND gate. According to these equations, we need an inverter here. According to these settings. So this output goes to a counter. This is an n-bit counter that also specifies the size of the multiplexer, sorry, the ADC converter. So the output of this n-bit converter, can anyone guess कि ये किधर जाती है? कोई बता सकता है ये n बिट्स किधर जाती हैं? किसी का कोई देन में आ रहा हो कि ये इनपुट्स किधर जा रही होंगी? नहीं? ओहो. They go to, let me draw this, a deck. So they go to a deck. So basically, start of conversion is over here. That start of conversion signal is over here. start of conversion signal is reset for this. So for any fixed analog input, because it is coming from sample and hold circuit, it will be fixed. So for any input signal, input voltage that is fixed and it's non-zero input, when you say start of conversion, the counter will start reset, and as soon as we say reset, this output is zero. Why this DAC output is zero? Because all inputs are 0, 0, 0. So when you have all input 0 to a DAC, DAC output is 0, 0, 0. So that output 0, 0 goes back to this comparator, and since this 0 is this will apply. So this output will be greater than this. So this output will be 1. It will start from 0. Input will be 0, 0, 0 and zeros over here. And output will be 0 volt. That's the job of the DAC here. So this output will be, of course, less than any non-zero analog input. So this output will become 1. And as a result, this output will be, 0. As a result, this will be 1. When V in 1 is greater than V in 2, output is 1. All right, so let's remove this. So this is the case. This is greater than 0 output. This is 0 volt. So this output is greater than this. So this will apply. This will be 5 volt, logic 1. This logic 1 would, what will happen जब ये logic 1 होगा, क्या होगा? Anyone? हाँ जी, क्या होगा भाई? कुछ सोचिए, आप तो समझ आना चाहिए आपको वो ये सर्किट क्या कर रहा है। हम सब ने डैक भी पढ़े हुए हैं, काउंटर्स भी पढ़े हुए हैं, कंपैरेटर भी पढ़ लिया। पता ही है आपको, कंपैरेटर पढ़े हुए हैं हमने। कोई बताएगा बच्चा? एनीवन? कोई सारे सो रहे हैं शायद। अमैर जाग रहे हैं, सो रहे हैं?
जी सर, इधर ही हूँ।
हाँ बताएं, कंपैरेटर पढ़ा हुआ है?
सर वैसे पता है वो कुछ स्पेसिफिक, आई एम नॉट श्योर किस तरह पढ़ा होगा।
ऑप एम्प्स का कोई ब्लॉक डायग्राम, ऑपरेशन एम्पलीफायर्स पढ़े हैं एज ए ब्लॉक डायग्राम, नॉट डीप इनसाइड दैट्स अ कॉम्प्लेक्स सर्किट, बट आपने ब्लैक बॉक्स के तौर पे पढ़े हैं ईमान?
सर्किट्स लैब में था शायद पिछले सेमेस्टर।
Right. So this is a mathematical model, simple MATLAB type model of analog comparator, that when input is written here, that the when input is greater than V in 2, output is 1. Very simple. And when it is less than this, the output is 0. Now अब इसका कौन बताएगा? इस सर्किट को देख के बताएंगे क्या होगा? कोई सोच रहा है इसके ऊपर? इसका क्या फायदा पढ़ने का अगर आप लोग खुद भी ना थोड़ा सा इंजीनियरिंग अपनी लगा सकते हो कि काउंटर 0 से स्टार्ट होगा और एंड गेट की एक इनपुट 1 हो जाएगी, तो क्या होगा? ईमान? ईमान बताएं।
सर
मैं बताता हूँ, वो अच्छा नहीं लगता हर चीज, कुछ आपको सोचना चाहिए। हाँ भाई, कोई और? जमशेद?
यस सर।
हाँ, आपका ख्याल कुछ समझ आ रही क्या होगा?
सर थोड़ा थोड़ा आ रहा है बस, बाकी कंफ्यूज हूँ।
आप बताएं क्या हो रहा है, क्या होगा?
सर आई थिंक एक पॉइंट आएगा जब एनालॉग वाली जो है इनपुट, वो उसकी वैल्यू लोअर हो जाएगी एज कंपेयर टू द डैक आउटपुट।
हाँ, फिर क्या होगा?
सर वो फिर कंपैरेटर की आउटपुट 0 हो जाएगी आई थिंक।
फिर हाँ, वेरी गुड वेरी गुड, अच्छा है। आई थिंक क्या सही कह रहे हैं आप। फिर 0 हो जाएगी तो क्या होगा काउंटर को?
सर एंड गेट की फिर आउटपुट 0 हो जाएगी। उसके
तो
बाद उसके बाद कंफ्यूज हूँ मैं कि उसके बाद क्या होगा।
काउंटर की इनपुट, ये क्या है इनपुट उसकी काउंटर की?
एंड गेट की आउटपुट है आई थिंक, काउंटर की इनपुट है।
सर क्लॉक है
क्लॉक
काउंटर।
इनपुट है, काउंटर की क्लॉक है। तो हाँ भाई, ये किसने कहा था ये क्लॉक है? कौन था ये?
सर ईमान।
ईमान? हाँ
जी
जी, अब क्या होगा बताएं, शुरू से दोबारा बताएं क्या होगा।
सर जब तक कंपैरेटिव लाइक एनालॉग इनपुट जो होगी वो हायर होगी डैक की आउटपुट से, तो 1 जाता रहेगा और काउंटर इंक्रीमेंट होता रहेगा,
अच्छा,
उसे क्लॉक मिलती रहेगी। फिर जब एक पॉइंट आएगा जिस पे डैक की आउटपुट है जो हायर हो जाएगी फ्रॉम द एनालॉग वन, तो फिर क्लॉक 0 होगा, तो इसलिए काउंटर स्टॉप हो जाएगा।
वेरी गुड, बहुत अच्छा है, जबरदस्त। तो बिल्कुल यही चीज उन्होंने बताई। बात मेरा ख्याल वो काउंटर को काउंट करना, ही डिडंट टेल अस के काउंटर काउंट करेगा। तो it will start counting as soon as this is as soon as SOC comes in. This is less than this, so output will become 1. So clock will rush through to the counter. It will get to go ahead, go to the counter. So see then the the great use of the AND gate. So this counter will start counter will start incrementing. Is an up counter. So it will start incrementing, and as a result, this count will start, and the output over here will start to increase with every clock cycle. So it will increase until it passes V in. When it passes beyond V in, then this will become 0. And the counter will stop. So you can say that in a way, this output over here is, if you want, you can invert this output is end of conversion. So when this output becomes greater than this, you have this going from 1 to 0. So this AND gate is closed. The gate is closed. So no gating of the clock anymore. So counter output stops. At that time, this output over here, you wait for the output to become low. So when it becomes NOC becomes high, then you can read this output. This is N bit ADC output. नजर आ रहा है ना इधर? So this will be then your N bit ADC out. So this is very simple and very clever. Can't say it's very clever, very simple circuit. So this is called the staircase ADC. So basically, it will take 1 microsecond. By this speed, it will take 1 microsecond to rise. After n microseconds, it will move beyond the analog input and the output will stop. So higher is the analog input, higher is the number of clock cycle it will need to go beyond the analog input, and higher time it will take to convert. So let's use a mathematical example here. Example. This is 1 megahertz. Clock is 1 megahertz. Equal to 1 microsecond time period. Because one over 1 megahertz is equal to 1 microsecond. So say for example, V range is 0 to 10 volt. That is basically the range of this DAC DAC. That output can go up to 0 to 10 volt. So if input is 000, DAC output is 0, and if input is 1111, DAC output is V range. So DAC output is 0000. The DAC output is 0 volt, and when the input is 1111, DAC output is V range. That in case is equal to 10 volt. याद है ना, डैक की आउटपुट मैक्सिमम होती है जब सारी इनपुट 1 हो, और वो इसके डिजाइन में हार्डवेयर डिजाइन है इसका, जो कि सर्किट डिजाइन बताता है कि ये कितने पे मैक्सिमम आउटपुट क्या होगी. इट डिपेंड्स ऑन द पावर सप्लाई of the DAC. So it could be 10 volt, it could be 12 volt, it could be anything. It depends on the power supply of the DAC. I chose 10 because maybe it will easy to do some mathematics. Maybe it will help us to do some mathematics. So now the time to assume some size of the ADC also. That is the size of the DAC. Size of ADC also the size of the DAC. So n bit ADC bits equal to कितनी करें बता दें, 10 ही कर देते हैं, 10 bit ADC. So then 2 raised power 10 will be nearly equal to 1000. So 10 bit ADC. DAC. So now the step size कितना होगा इस DAC का? Delta is equal to 10 volt divided by 2 raised power 10, which is nearly equal to 10 volt divided by 1023 होना चाहिए, तो हम 100 ही कर लेते हैं, होना 123 चाहिए.
सर 1023 से 9.78 मिलीवोल्ट्स आता है।
ओके, तो अगर 1000 हो तो जरा करीब हो जाता है। 1023 से दिस इज नियरली इक्वल टू दिस इज इक्वल टू एग्जैक्टली इक्वल टू 9.7
78 मिलीवोल्ट्स।
मिलीवोल्ट। तो अगर मैं इसको 1000 अप्रोक्सीमेट करूं फिर कितना आता है? 10 मिलीवोल्ट। तो ये अप्रोक्सीमेट हम कर लेते हैं 10 मिलीवोल्ट। पेपर में आपने अगर आपके पास कैलकुलेटर है तो आप इसको एग्जैक्टली कैलकुलेट करें। 2⁻10⁻1। तो -1 24 और 23 में तो एब्सोल्युटली इतना फर्क पड़ता ही नहीं है, बिकॉज दिस इज 10 इज वेरी लार्ज। सो 24 और 23 में तो इतना फर्क वैसे ही नहीं पड़ेगा। बट बहरहाल द एक्चुअल मैथमेटिकल फार्मूला इज दिस। सो फ्रॉम डेल्टा यू कैन सी कि ये टाइम लगेगा। एंड नाउ इज द टाइम टू assume some input voltage. So we input को assume करें। assume सारी assumptions ही हैं, लेकिन ये चूंकि ये values given है तो they are no assumptions, not assumptions anymore. So V in is equal to कोई voltage बताएं जो कि हमने convert कर दी। कोई voltage बताएं उसामा आलम। Any voltage we need to convert? It should be less than 10.
Sir, 8 volts.
8 volt। 8 point पूरा 8।
Sir, 8.0. Pura 8.
8.0 पूरा 8। ऑलराइट। सो 8 वोल्ट्स में पहले तो हमने देख लिया कि कितने स्टेप्स आते हैं, बिकॉज दैट विल बी द नंबर ऑफ स्टेप्स दैट दिस विल टेक, द काउंटर विल टेक टू काउंट। सो द स्टेप्स आर deltas are steps in this equal to 8 volt divided by 10 millivolt। एक स्टेप 10 मिलीवोल्ट का है तो 8 वोल्ट में कितने स्टेप्स होंगे? इसको इसको
Sir,
मल्टीप्लाई बाय
800.
8 वोल्ट भी करें तो ये आ जाता है 800 स्टेप्स। और 800 को स्टेप्स हैं तो ये आपकी बेसिकली क्या होगा कि इट विल स्टार्ट काउंटिंग। सो व्हेन इट बिकम 001, वेरी इंपॉर्टेंट ये देखें कॉन्सेप्ट कि व्हेन इट गोज फ्रॉम 00 टू 001 बैक आउटपुट विल बी 10 मिलीवोल्ट। 0010 to 20 millivolt, 010011 30 millivolt. If it is counting 10 millivolt, 20, 30 millivolt, 40 millivolt, and so on and so on, until it will reach greater than 8 volt. So ये सीढ़ियां चढ़ेगा, ये आउटपुट जो है ना 10 millivolt के बेबी स्टेप्स लेगी। It will take baby steps until it hits 10 millivolt. तो बेबी स्टेप देख लें, बेबी स्टेप भी आखिरकार बन ही जाते हैं। बेबी स्टेप्स लेके भी बंदा कहीं ना कहीं पहुंच जाता है। तो मतलब ये कि देखें एक लेसन आपकी जिंदगी के लिए यहाँ से आ गया कि डोंट ट्राई टू टेक लॉन्ग स्टेप्स। समटाइम बेबी स्टेप्स कैन गेट यू टू योर डेस्टिनेशन। आ गया, समझ आ गई? तो एवरीथिंग हैज अ मीनिंग इन लाइफ आल्सो। So here you can see here all these small little baby steps can get you beyond this 800. So how long will it take to go there? That's the question. That is the problem. इसमें आपने फाइंड करना है कि कन्वर्जन टाइम कितना होगा। कन्वर्जन टाइम ये नीचे करना यार थोड़ा सा। 800 स्टेप्स लग रहे हैं तो जाहिर है एक स्टेप 1 माइक्रो सेकंड का है, तो कन्वर्जन टाइम विल बी 800 माइक्रो सेकंड, well almost less than a millisecond. So worst case टाइम क्या होगा जी? वर्स्ट केस टाइम क्या होगा? वर्स्ट केस टाइम होगा जब इनपुट मैक्सिमम होती है, तो यू हैव टू टेक लॉट ऑफ बेबी स्टेप्स टू रीच टू द मैक्सिमम। तो अगर इनपुट 10 वोल्ट है, you will have to take 1,023 steps to get to the 10 volt value. So that would mean that it will take 1000 microseconds or 1 milliseconds. So worst case time for this will be 1 millisecond. Worst case time is 1 millisecond. For V is equal to 10 volts, and that is 1000 microseconds, nearly equal to 1 millisecond. So the best worst case worst case sampling rate क्या होगा? That's the how many time samples you can take in a second. So sampling rate is 1 over conversion time. इधर कर लो यार, नजर आ रहा है? 1 over conversion time. So worst case conversion time in this case is worst case conversion frequency sampling rate will be is equal to 1 over conversion time worst case equal to 1000 samples per second. This is your worst case time, 1000 samples per second. And that's the one drawback is that this time is too high. So usually this is used, this kind of ADC is used in multimeters where you touch a multimeter and you can wait 1 millisecond का तो आपको पता भी नहीं लगेगा and you get the output. So लेकिन it takes time. Multimeters वगैरह में वो human आ जाती है involvement. But when you want to convert some signal using some DAC for audio or speech, you cannot really have cannot wait this much time, 1 millisecond. Although you know, if you look at this speech signal, which is if it is band limited to say 20 kilohertz, the maximum sampling frequency you need is 40 kilohertz, and 1 over 40 kilohertz is less than this worst case sampling time. So you cannot use this for speech. So that brings us to the second type of ADC. This ADC is, it reaches there, and as you can say, it is a ceiling type because when the input of the DAC is greater than the input, so it basically samples to the next sample point, next point on this characteristic. So it takes थोड़ी सी भी ज्यादा होगी भी इन इससे तो ये काउंटर एक एक्स्ट्रा इंक्रीमेंट होगा, क्योंकि कंपैरेटर जो है ये तो ओपन लूप कंपैरेटर तो नैनो वोल्ट्स पिको वोल्ट्स में भी कंपेयर करके आउटपुट जो है वो लॉक कर देता है. So if this is slightly greater than that, output will be locked to the next level. So anything between this step 10 millivolt step boundary के ऊपर थोड़ी सी भी आउटपुट होगी तो नेक्स्ट लेवल पे लॉक हो जाएगा. सो दिस इज बेसिकली अ सीलिंग एडीसी. कहाँ लिखूं? छोड़े, इसको लिखते ही नहीं, ऐसे मैं कहीं लिख दूंगा, कंफ्यूजिंग हो जाएगा. So the second type of ADC is this ADC is sometimes referred to as what you can say. थोड़ा नीचे कर दूं. Zoom out. Right. So this is sometimes referred to as a serial search. So like in a dictionary, if you want to find a word with starting with letter W, so what you do in serial search is you look at the first page, second page, no, third page, no, and you go on until page by page, step by step, baby steps. You go on incrementing the this table count, page count, until you reach the page on which the word that you are looking for is there. So this is called a serial search. So ADC is akin to a serial search in कंप्यूटर साइंस. एक सीरियल सर्च होती है, दूसरी कौन सी होती है? व्हाट इज क्लोज टू सीरियल सर्च? सर्चिंग नहीं पढ़ी आप लोगों ने? हैं? लोग बताते नहीं, चैट में राइट कर दें अगर आपने बोलना मुश्किल हो रहा है. यू आर लास्ट योर टंग इज टाइड, कांट से एनीथिंग. You can always write in chat window. Come on. What is the second type of search? Serial search and कुछ नहीं पता.
सर नहीं पढ़ा.
Parallel search. पढ़ा ही नहीं. No. The second type of search is called binary search. Binary search. So binary search has this is way more efficient than serial search. Way more. The first thing that with binary search is that no matter what word you are looking for, you will find that in fixed n steps, where n is log to the base 2 the total number of pages. If there are 1000 pages, so n will be 10. If there are 2000 pages, n will be 11 steps. So it should be less than 2 raised power n. Say if this is the number book that you are looking for. So how will you reach to the n steps? For example, you are looking for some letter starting with the Z. So you break your book in totally half. So now look at this. This number is starting with n. So that would tell you that the number should be z is greater than n. Those are the numbers must be in this half. So you forget about this half. So half of your work is already done. Sorry, half of the search space, not the work. The search space is already done. Now you break this exactly this part into half. Now you reach q, for example. Q is less than z, so you know that it is not there, it is there. Say the word is starting from, मैं change कर रहा हूँ, it's starting from W. थोड़ा change कर दिया. So now you break this again. You reach a point where the word is starting with Y. So Y is less than, greater than W. So you discard this half. Because now you know that it is greater than this Q and it is less than Y. So the word you are looking for must be in these pages, in these few pages. So you keep on dividing this, and if it is greater than the number you are looking for, you discard this side. If it is less than the number you are looking for, you discard this side. So until you zoom in like a missile, like a laser guided missile that goes uh, after a plane or of an aircraft, you zoom into your target. So within n steps, you are on a page W where the word you are looking for is present. So it takes only n steps. Even if the word is on the very first page, the problem is this. Even if the word is on very first page, you have to do the same. You start from here, you know it is less, so you discard this. You start from here, it is less, you discard this. You start from here, it is less, you discard this, until you reach to the very first page. So n step, it will always take n steps. And that is very much liked by computers, because computers like things that take fixed amount of time. So n steps. So if it is a 10-bit ADC, for a binary search ADC, it will take n steps. So 10-bit means 10 microseconds. So every sampling will be done in 10 microseconds. So in an ADC, 10-bit ADC, what we do is we only change this part of the circuit here. And this time we have here is a state machine. This state machine is sometimes called, this type of ADC is called successive approximation ADC. Successive approximation ADC. Why I don't know why मेरे से पूछा नहीं उन्होंने, मेरे से पूछते तो मैंने कहता कि भाई ये नाम ठीक नहीं है, इसका नाम रखें बाइनरी एडीसी. लेकिन बहरहाल वो उन्होंने they didn't know, कंप्यूटर साइंस वाले लोग नहीं थे, उनको बाइनरी सर्च का चूंकि पता ही नहीं था जिन्होंने ये एडीसी बनाया. It came before, much before, I think, the concept of binary search. Clip कर देना. So successive approximation ADC. It successively approximate input. Successive successive approximation सो दोनों लफ्ज काफी लंबे हैं। ADC, अब मैं पूरा ये तो पूरा नहीं लिखूंगा। एनालॉग टू डिजिटल कन्वर्जन, सक्सेसिव अप्रोक्सीमेशन ADC. The only thing is that replaced here is this is called state machine, or sometimes it is called successive approximation register. Other are same. No change in rest of the stuff. So start of conversion signal comes to this state machine. When start of signal inverter signal comes to this state machine, what are the outputs? Outputs are not 0, 0, 0 in this case. Outputs are when the start of the conversion comes, the output of the state machine is uh, uh, output of state machine is output of state machine is 1000. Say if it is an 8-bit ADC, output will be 100, or a 10-bit ADC, output will be 100. So coming back to the same example, so 100 will give rise to this DAC output. DAC output क्या होगी? So this will be the start of conversion. Output will be 1000. जरा zoom कर देना इधर पे। या ठीक है रहने दो। So what will be the DAC output in this case? 10 वोल्ट रेंज का ADC है, तो आउटपुट क्या होगी? अगर MSB 1 हो जाए तो आउटपुट क्या होती है?
हाफ होगी 5
हाफ होगी। वेरी गुड यार, वेरी गुड। Honestly, I'm very this is good. So 5 volt, because this has a weightage of 5 volt. Say we are searching for 8 volt. Is this voltage less than 8 volt? Is this voltage less than 8 volt? Yes. If this is less than 8 volt, the state machine will keep this as 1 and it will try the next step. It will keep this because that means this 8 volt has the voltage of 5 volt within this voltage. That means it has this weightage present in this 8 volt. So it will keep the 8 volt voltage there. And you try the next bit. So next time the output will become 1100000000. Now this one will make the DAC output कितनी हो जाएगी?
सर 7.5
Very good, 7.5. Half of this will be added. Remember, voltage आधी आधी होती जाती हैं वेटेज के हिसाब से। इसकी वेटेज है 500 है, अगर 1000 स्टेप लगाएं तो इसकी वेटेज है 512, इसकी 256 एंड सो ऑन। सो डैक की आउटपुट भी उसी तरह से आधी आधी है। सो 7.5 वोल्ट इज लेस देन 8 वोल्ट। So it is going to keep this also. Okay, this is less than this. So it will try the next bit. So now what is the DAC output? That will be
8.75 8.75
8.75 volt, which is greater than 8 volt. That means this bit should not be present in this. So successive approximation circuit will bring this back to 0. इट विल ब्रिंग दिस टू जीरो, क्योंकि ये तो आउटपुट बड़ा कर रही है। सो हमने आगे नहीं जाना अपनी बुक में, सर्च में हमने पीछे जाना है। सो इट विल ब्रिंग दिस टू जीरो, सो दिस विल बिकम 1 1 0, and then it will try the next output 1 0 0 0 0 0 0. It will make sure that when this is 1, this DAC output is less than the given output. So what will this be? The weightage of this is, let's write down the weightages here. Weightage of this is 5 volt. MSB is 5 volt. And so next is 2.5 volt. Then next is 1.25 volt. Next is half of this 0.625 volt. Next is half of this, which is 0.3125 volt. So basically, this successive approximation is going to find all the voltages. The sum of those voltages is less than this volt. It will make sure that we never reach this. So it will try bit by bit. So this, since this bit has made this greater than 8 volt, it will return this to 0 and try the next bit. So next will be removing this 1.25 volt को वो remove कर देगा, because this has increased the input, and it will try the next 0.625. So 7.4 5 volt plus 0.625 volt किसके बराबर होता है? हाँ भैया किसके
8.125
बराबर?
125
8.125 volt, which is again greater than 8 volt. So this is also not present. Interesting example है. So it will try the third, इसको भी zero कर देगा, and it will try the third one. So 1 1 1, इसको भी वो zero करेगा. It will return this to 0 and try the next one. So ये one try करेगा. So what is by trying this, what is now, इसमें से आप 6.625 निकाल दें, क्योंकि वो तो वेटेज शामिल नहीं है, और 0.3125 ऐड करें. व्हाट डू यू गेट? सब्ट्रैक्ट 0.625 फ्रॉम दिस एंड ऐड 0.3125. क्या आता है आंसर?
सर 0.625 तो सब्ट्रैक्ट नहीं होगा, 1.25 वाली भी तो 0 है.
हाँ हाँ, वो तो पहले ही सब्ट्रैक्ट हो गया हुआ. हाँ ठीक है, वो तो पहले इसमें से ही करेंगे ना सब्ट्रैक्ट,
अच्छा सही है.
क्योंकि ये वाली तो 0 हो गई थी. वी रिटर्न बैक टू दिस वन एंड वी ट्राइंग दिस वन ओवर हियर. So what will be the new voltage? 8.125 में से 0.625 निकाल के 0.3125 ऐड करें. अब क्या आता है आंसर? हाँ भाई,
सर 7.8125.
7.8125, which is greater than, less than 8 volt. See, it is trying, it is going to go for, ये वाला स्टेप नहीं चलेगा, ये नहीं चलेगा, उसने इसको जीरो कर दिया, ये ठीक है, क्योंकि दिस इज लेस देन दिस, तो ये वन वो कीप करेगा. So you see 7.85, we are getting close to 8 volt, but we are staying below 8 volt. We don't want to jump across 8 volt. So it will try the next bit. That will be 1 1 0 0 1 1 0 0 0. So now what is the output? 0.3125 का हाफ इसमें और ऐड कर दें, क्या आएगा आंसर? हाँ भाई, add point half of this voltage, 0.3125 का हाफ क्या होता है?
7.96875.
7.968. which is less than 8 volts. So it will keep this one. So we are getting very close to the number, slow by slow. We answer should reach around about 800. Total this binary output should reach to 800 because that was the answer we got the last time. It has 800 steps in this. So इसके बाद ट्राई करता रहेगा एंड सारे स्टेप अब मेरे पास टाइम नहीं शो करने का. इट विल ट्राई एवरी स्टेप एंड सी इफ इट इज लेस देन और ग्रेटर देन, लेस देन और ग्रेटर देन. लेट्स ट्राई अनदर स्टेप. This is greater than, so it will keep this and try another step. 1 1 0 0 1 1 1 0 0 0 0. So this one, what is this one adding into this whole scene? This one, third one. तो हम तकरीबन 6 कर चुके हैं, नहीं 7 कर चुके हैं, 1 3 रह गए. और नाउ एडिंग दिस इज एडिंग अनदर half of this. ये आता है 1 5 6 2 5. दो. Half of this is again 0.0 0.62500. That is the half of this.
सर इसका
तो
हाफ
ऐड करें.
सर इसका हाफ ये नहीं है 0.078125 है.
0.7078125. सॉरी, हाँ ठीक है ना, 78125 वो इसमें ऐड करें. 0.7968 में 0.078125 ऐड करें, क्या होता है?
सर 8.0468.
8.04 हो गया ना वो. That is also greater than this. And that is also greater than this. तो इसको भी फिर 0 कर देगा और अगला ट्राई करेगा, अगला 1 ट्राई करेगा. अगला 1 ट्राई करेगा तो वो किसके बराबर आएगा? तो इसमें से ये माइनस करें, वो ये बैक टू 7968. उसमें इसका भी हाफ ऐड करें 0.078125 का. तो वी गेट टू द नंबर दैट वी आर लुकिंग फॉर. मतलब ऐसा करते जाएंगे. चले इतना ही अगर समझें तो ये 11001101 ये किसके बराबर है इन डेसिमल? चेक करें. 11001101. व्हाट इज दैट इन डेसिमल? इधर करना यार जरा. 1100110100. 10 नंबर का ये अप्रोक्सीमेटली फर्ज करें ये आंसर आया अप्रोक्सीमेटली. व्हाट इज दिस इन डेसिमल? ये है 512 प्लस 256. मैं ही करूंगा या कोई है मुझे हेल्प करने वाला? 512 प्लस 256 8 6 768. ये दोनों नहीं है. प्लस ये कितना है 128. 512 256 128 64 32 plus 32. 768 plus 32 0 9 7 790 plus 16 plus 16 806. So this error is I think coming because we in the previous example we took 1000 steps, not 1024. We had taken 1024, we had reached somewhere about 806. So you can see we are near 1806 answer. That is the right answer when you convert this. So these weightages will add up until this answer is less than. And remember, it will try the last bit also. And if that also makes the number greater than this, it will change that also to 0. It will not keep that 1. So it will change last bit, check also the last bit, and if that is also greater than, makes the answer of the DAC greater than the input, it will change that also back to 0. So in a way, it works on a flooring function, because it will give you final answer such that the DAC output is less than, almost one step less than the input voltage. So it will go further, and number of steps it will always take. तो देखे ना, इसने 5 वोल्ट ट्राई किया तो ऑलरेडी 8 वोल्ट के कितने करीब ये पहुंच गए। 2 स्टेप में ये 7.5 वोल्ट इज वेरी क्लोज टू 8 वोल्ट, और 3 स्टेप में 8.125 वोल्ट इज also very close, and it is slowly it is reaching up to this 7.8125, then 7.9, already it is very close to that. So अभी 3-4 step और हमने करने हैं, so it is going to hone into the input voltage. So we'll get the right answer after 10 steps. The beauty of this is that it takes exactly 10 steps and gives you the answer. No matter whatever is the input, the answer is always ready in 10 steps. And if you're running this at 1 megahertz clock, this state machine will take 10 clock cycles to give you the answer, which is equal to 8 microseconds. So the conversion time is always same. Conversion time in successive approximation is N over F. Conversion time is equal to N over F, where N and F is the frequency. So its conversion time is fixed, N over F. इस पे zoom कर देना यार, conversion time. ऊपर करना था, हाँ ये. So conversion time is N over F C into CT, where F is the frequency. And that means that it has much higher sampling rate. It has only in engineering, you give something, you lose something. There is always a bargaining. There is always a give and take. So you are giving a very good fixed time conversion system. What you are losing, what are you losing? Losing is that you have to design a brain here, which is the state machine, the successive approximation register that you need. Yeah. So it's like that. So you have to go do little bit ज़्यादा brain डाला इसमें, तो आपका conversion time कम हो गया. लेकिन direct use of the brain का direct use है यहाँ. Okay, so that's the end of today's lecture. So next time we'll embark upon another journey, which will be the last topic in our course, and that is assembly language programming. So thank you very much. Question पूछ लें जल्दी से, कोई जो पूछ लें.
सर वो लैब 9 का जो बोनस टास्क था वो आपने कहा था क्लास के बाद थोड़ा सा बताऊंगा कि वो क्या करना
क्या था यार बोनस टास्क लैब 9 में?
सर उसमें अजीब सा लिखा हुआ था, वो समझ नहीं आया था मुझे.
हाँ देख के भी बता देते हैं आपको. What was the lab task 9?